How is everyone? Okay. Do this right. Computer documents. Okay. All right. So homework 10 is due today. How are we doing with it? I received comments saying that it's getting too hard. Is it? Are we okay? You know what I replied to that? So wait until this week's lecture. Okay, so this is something that happens, very often, or I would say almost, as you reach the final 1/4 of the semester. It gets a bit overwhelming because not only is the material comprehensive, it's comprehensive in a way that you have to remember all the things. The picture gets bigger and bigger. You need to know all the things to understand where you are and how you move up, right? So that's the overwhelming part. Okay, so we have one more week and then there's the break, and after the break we'll have 2 more weeks of classes. So my current plan now is to finish up to transportation problem, and we will not touch game theory at all, because I was hoping I could cover 2-person zero-sum game and getting to the settle point. Then you see the duality theorem becomes so clear right there what it's all about, but we don't have time to get into that. If you're curious, you can read the book. It's all there. All right? So some perspective. Okay. We'll finish chapter 5 today. We've been talking about this sensitivity analysis. That is, we have an original LP problem we solved, we find the optimal solution, and then now we make a little change here and there. We want to see how the solution responds to that. Okay, so we talked about changing in many things, and today we're gonna make one specific change, and that will be the last thing in that part. That is, we will add a new constraint. Okay, so add a constraint and see how the solution changes. So you have an original, let's say, the old LP problem, the original one, you solved it, and then you have an optimal solution already. Let's call it X with a star. You have an optimal solution. And I add a new constraint. And what happens? You can think a little bit about it before we dive into what to do. Let's say you have an old problem. How about we just like think of a 2-dimensional problem so we can sketch like the feasible region. How about I do some feasible region? Let's say this is the feasible region of some problem, okay? And then the old one, the old LP problem, and you solved it, and then you find out that is the optimal solution. Let's say the minimum is attained right there in the corner. Usually they're at the corner. And now you add a new constraint. So what does the new constraint do to the feasible region, for example? So new constraints, if you set it to be equal sign, it's a line. Is that right? In the two-dimensional setting. And if you have bigger than or smaller than, so usually you have a line, and then on one side of the line is feasible, on the other side is not feasible. Is that right? So it kind of will like cut through here. So let's say I add a new constraint, just pure for illustrative purpose. Let's take a green. Let's say my constraint is like this. I have a new constraint like that, and the part on the right is feasible for this new constraint. So what it does is that after the new constraint, I have this feasible region, and the X star is still in it. Do you think the optimal point will change? Do you think the optimal value will change? What do you think? Will it change? How do you find this? It's some kind of a contour line that you come down and you hit it first. Will that fact be changed? No, because this is still a feasible point, isn't it right? That will still be the minimal. Is that clear? So if that is the situation, actually, there's nothing to do. So I have a discussion here. If X star satisfies the new constraint, meaning it's still in the feasible region, what can you say? Well, I know X star is still optimal. That fact remains, and so is the optimal solution. No change. Optimal value remains. Right? It makes no change whatsoever. Okay. And now, in the other case, if the constraint is so bad that X star fails the new constraint. That means it's not feasible anymore, so it's quite clear it cannot be the optimal solution. You have to find something new, right? So, new optimal solution is needed. So you have to solve it and find out. So for this example, you could think that I add a new constraint. Let's say I draw with yellow. Let's say my constraint line is like this, and the part under is feasible. So now my feasible region will be the part under, and X star is being cut out. It's not feasible anymore. All right? Is that clear? Okay. So what we will do is to go through one example, bless you, and then for this example, we will add different types of constraint and hopefully covering different scenarios that can happen. Okay, so let's take an example one. Well, actually, it's the same example. We're going to add different constraints. So let's just say example, and then we'll add different new constraints. So, okay, so this is a solution of a linear programming problem that we solved, and we have the final tableau, which I will present here. So the F tableau, and then I will write it out. Okay, so there you will be minimizing negative z. So it's actually maximizing z here. Okay, I have these constraints. -2, x1, 5, x3, x4, 2, x5, x6 equal 6. I think this is from one of the problems that we talked about earlier. It's okay, some numbers. So these are the two constraints. Let's label them 1 and 2. And you see it's in canonical form, and x4, x2 are the basic variables, right? Okay, and then have the objective function here, 3x1 2x3, 2x5, x6. Okay, so it's 106 from that example we had earlier. So that's the objective function. Okay, so there we solved, so we know the z max, the minimum of negative z, now is 106, attained at the optimal function. The old optimal point solution is 0, x2 is 4, x3 is non-basic, x4 is 6, right? x5 is 0, x6 is 0. Is that okay? Okay, now let's add a constraint. So part 1, let's say part 1 now, add the following constraint. Let's write it. 3x1 plus x2 plus 3x4 less than 20. Okay. So the constraint has a less than equal sign. Let's call this constraint C1. So you know you have to add it in the tableau. Now you have the third row in it, right? So you will add slack variable and rewrite it into the following. Oh no, wait a second. Before we do that, we need to first check if x star satisfies C1 or not. If it does, then nothing changes. Is that right? So check if x star satisfies C1. Well, that's a simple computation. So that's 0, that's 4, and that's 6. 3 times 6 is 18. These adds up to be 22, and it's required to be less than 20. So does it satisfy? No, it doesn't, right? So I need to find a new optimal solution. Okay, so now what do we do? Okay, so let me add a slack variable. Add slack. So I already have x6, so let's say x7 is the slack variable I add. So I have 3 x1 plus x2, 3x4 plus x7 equal 20. Okay, so the C1 constraint now is a little bit changed with the slack variable, so C1 prime. And I would add this to here in my constraint. So now my constraint will be 1, 2, and C1 prime. And looking at that, I see that this is messing up my basic variables, because using 1 and 2, I know x2 and x4, they are well pivoted. These are basic variables. But then you add one more. This one contains a non-zero x2 term and a non-zero x4 term. Then those two are no longer basic variables. Is that right? It messed that up. So I would like to do manipulation, meaning I would like to remove x2 and x4 in this expression so that they can be still the basic variable. Is that clear what I do? So I want to remove x2, x4 in C1 prime. How can I do that? Well, an obvious thing is you could write x2 in terms of all the other and plug it in, right? And you write x4 in terms of all the other, use the first equation and plug it in, and then open it up and collect like terms. Can one do that? Would that be simple? So, okay, so what you could do, or you can do other ways. So you can simply plug in x2, meaning from equation 2, and x4, you can get it from equation 1. You can plug that in C1 prime. And you can clean it up, all right? So if you shall do that, is it okay I skip that detail? It's just opening up and recollecting terms. And later on, there will be good news on that step. So let me don't give it to you right away. So I have the following. After some cleaning up, I get that. 3x3 plus x5 minus x6 plus x7 equals -2. Now I write the new constraint in terms of variables that does not contain x2 and x4. Okay, let's call this C2 double, or C1 double prime. This is C1 I'm talking about, C1 double prime. So I see if I collect the constraint 1, constraint 2, constraint C1 double prime, collect all these three together, I see that they are in canonical form on the left-hand side. Canonical with the basic variables. So I have x2, x4, x7. Is that right? So the only thing now is that it has a negative number on the right-hand side. Did we talk about how to handle that situation? What would you use? The dual simplex. Is that right? That's exactly designed for this situation. So I will solve it with the dual simplex. So I will turn this on in the LP Assistant and let's see. Computer, PC. Okay. So let me bring that down. Oh, it goes in the middle. Oh, it's going to block what I have. I thought it was on the side. No? All right. Then I have to deal with you. Okay. Okay, it's warming up. I am going to put the numbers in the LP Assistant as it warms up, so you will see. New regular metal B. What is metal? No. No. Source. Yes, I did. Come on. It's coming? All right. Okay, so here I open the LP Assistant and let's see how many variables will we have. All the way to x7, right? So I need to add a couple more. Add one more, one more, and one more, and I have one more constraint. Is that right? So what I'm going to show you would be I will put in the old constraint. Let's see. Let me finish that first. So I put in the old constraint. One thing at a time, otherwise I'll punch wrong numbers. -2, 5, 1, 2, -1, right? And the right-hand side is 6. Second equation, right-hand side is 4. What do I have? Let me come over here. I have 11, 1, -18, 0, -7, and 4. That's the second equation. Is that right? And the objective function from that, well, let's put it in 3, 0, 2, 0, 2, and 1, and that is 106. Okay. So that step that I skipped the detail, I say you could just find the expression for x2 and x4 and plug it into that constraint and work it out. You actually don't have to do it by hand. You could easily use the LP Assistant to help you doing that. That step is nothing but pivoting, okay? So what I will put in the new constraint here, will be the constraint that you just add a slack variable, and that's it, okay? So if you go to C1 prime, this is what you have. 3x1, 1x2, and 3x4, is that right? And then an x7, and the right-hand side was 20. Is that clear? I just put that constraint in. I mess up the left-hand side. Now it's not in canonical form, but I'll show you how to get out of it. So let's scan through. And then I see that x7 actually is already good. It's a basic variable, so let me select that. But then for this equation and here, I don't have any other basic variable. It's not canonical for any other, right? Okay? I deal with it. So let's go to pivot. So I remember that x2 was a basic variable here. And I want to make it the basic variable at the same spot. So, you know, when you click in this algorithm, all it does is it just pivot right there, isn't it? If I click here, what it will do will be it will make this guy 0, somehow rearrange it. Is that right? So let's do that. So now I have this tableau. Let me open the window a bit bigger so we can see. Now you see x2 is a basic variable. Okay? Now I go back here and make x4 a basic variable by pivoting here by making this guy 0. So if I click there, now I have x2, x4 as the basic variable. Now if you look at the third row here, the simplex algorithm generated this third row. Don't you see that is exactly the C1 double prime that we put on the table on the blackboard? So all that work can be done by just 2 clicks in there. Is that clear? So you don't have to do heavy work. So you shall be like, you are the mastermind. You have, I don't know what you want to call them. You tell them what to do and the things will be done. But you have to give the correct order. Okay? Okay, now I see I'm in the situation, the A is canonical, but I have negative B's, so I need to use this dual simplex algorithm to solve it. Do we still all remember that, the dual simplex? That exactly handles the situation, right? So looking at -2, that's the row I will pivot, and the candidate will be -1 and -2. So I'll be checking the ratio. For -2, I get -1.5, and -1, I get -1. So where do I pivot? Where do I pivot? Anybody? I should give bonus points for everyone who answers questions, and you all answer questions. The power of bonus points. Should I pivot at -1 or -2? Do we have consensus? I only click if we all agree that's where I pivot. Is there where I pivot? All right, click on that. And now I have a new -B I need to deal with. So I scan, I see 2 negative numbers here. For -3, I have ratio -1. For -6, I have the ratio -0.8. I shall pick the one with the smaller absolute value. Is that right? So that's where I pivot. I click. Am I done? Have I reached the optimal state? Yes. You see, now they're all positive here, and it's all positive here, so that's the optimal number. Is that clear how it's been done? So is that good news that you don't have to get rid of x2, x4, you just do 2 clicks and that's it. Okay, so it's pretty nice. All right. So, okay, so the optimal value now is here attained at y1 and 2 will be 0. That will be, okay, that's x2, 1 and 2, 0. x3 is this one, x4, and x6 is that. All the others are 0. Okay, so then you can go back and write out your conclusion. Right, so the dual simplex, let me just finish it right here. It gives you the z max. It's just some number. Maybe I don't have to do this. 102/3. Obtained at a feasible basic solution 0, 0. If I copy those numbers over, 2 over 3, 6, 2 over 3, 0, 4, 0. That's taken from that final tableau in the LP assistant. Okay. So is that clear? What we'll have to do? Any questions? Stop me. Okay, so that's adding a constraint with the less than equal sign. The slack variable is immediately your basic variable, one of them for the new one. Now I'm going to add a different constraint. So the new constraint is now bigger than equal sign. So 4x1 plus x2 plus 4x4 bigger than 29. Okay. And you can easily go and verify that the old optimal solution, so we are still considering the old LP problem, okay? Not without this constraint. We'll take this problem again and we add a new constraint, still 3 constraints, okay? So you can verify that the x star, now this is my C2, okay? X star does not satisfy. You should always check, okay? C2. If it does, there is nothing to be done, okay? So don't waste your effort. Go by and solve it and find nothing's changed. You can already know it right here, okay? So you rewrite C2, you add a slack variable, and C2 changes into 4x1 plus x2 plus 4x4. So the slack variable will be minus x7 equals 29. This could almost be used as a constraint that I put in, and this could almost be a basic variable except this annoying negative sign. Is that right? I would like to have plus sign here. What do? I multiply the whole thing by -1. So I get -4x1 minus x2 minus 4x4 plus x7 equals -29. Is that right? That's the C2 prime with the slack variable. Okay. And still, you will have to get rid of these two. These are the basic variables for 1 and 2. You can do the same thing if I do it by hand. You can plug in those two expressions. So you can plug in these two from 1 and 2 and rearrange terms. If you do that, you get the following. -x1 plus 2, x3 plus x5 plus x7 equals -1. Now, it will be guaranteed this number shall be negative. If this number shall be positive, that means x star actually will satisfy that constraint, okay? So you will have to do work, which means, okay, let's go to LP Assistant and get some help from there. We can just click and click. So let me, so it's right there. So, okay, so I go back to this tableau. I'm going to remove all these computation, edit. So I have to change only the last one. Is that right? So I will put in the one after you add the slack variable, and I ask Simplex to LP Assistant to pivot and get rid of things. So -4, 1, and the right hand side is -29, and that is still good, but the rest, yeah, so I will not be changing anything from here. Is that right? Okay, so let's see. I'm going to pivot. pivot. Right. Okay, so I want to make this one a basic variable. No, I think I put some wrong number. Edit. There's something. Why this become -1? I put 0 there, didn't I? Let me see. Did I put in the wrong number? Yeah, it's 0. -1. The new constraint. No, there is a -1 there. Oh, sorry, I'm copying the wrong number. This is -1 is correct. So let me see. Did I get all the numbers right before I click? 4, -1, 0, 4. Okay, let's see. Okay, let's pivot. So I want to make still that a basic variable, so I'm going to click there. That is just to do pivot. And I want to make this a basic variable, so I'm going to click here. Now you see the last equation here is exactly the one I put on the board, say eliminate after eliminating x2 and x4. Okay? Now I have to pivot using the dual simplex. Make sure you're doing the dual simplex. So I have a negative number. This is chosen, but there's only one negative coefficient, so that's where I pivot, right? I click on that, and then I see I still have a negative number, and then I scan through all the coefficients. I don't find anything negative. What does it mean? What do I have to do now? Someone's whispering. Can the whisper be louder?
Is that unbounded for that problem?
That means the dual problem is unbounded, yeah. Which means the problem you're solving now is not feasible. Is that right? Do we all remember? If you have a negative b here and then all of these are non-negative, that means it's not feasible. Meaning the constraint you put in is totally not compatible with the old feasible region. It excluded everything in the old feasible region. So you don't have any feasible solution. Is that clear? All right, so that's that. And let's put that solution back up. Okay, so let's say now I solved it with the dual simplex method. And I found that it's not feasible, so there's no solution. Okay? Okay, let's add another constraint. So, let's add an equal sign constraint. Let's say x1 plus 3, x3 plus x4 minus 4, x5 minus x6 equals -18. Okay, so let's stress. You can easily verify x star, so let's call this C3. X star does not satisfy C3. Okay, and therefore you need to solve something new. So you know you can add this equation into the old constraint. So you have 3 equations now, 3 equations with variable from x1 to x6. And then you know this one doesn't have any x2. x2 can still serve as a basic variable. Then you need to figure out 2 other basic variables, right? You could do it by hand and manipulating here, or we can give it to LP Assistant and find the correct spot to click and get it into canonical form. Is it clear? So what I will be doing will be, I will use LP Assistant to pivot and get in canonical form. Okay, let's try that. let's see. I have to open that. Bring the screen down. All right. Let's light a bit. Okay. So that was, I have to remove all these tableaux. Go back to the original one. So that's the original tableau, and I need to change the last equation, right? So that is 1 and 0 and 3, 1, -4, -1, and then I don't have y7. I have to remove it, because remove variable 7, because I don't need to add slack, because it's equal sign, all right? And that is -18. Is that okay? So I put in the last constraint there. And then I see that this y2 is a basic variable. So let me select it. But I don't have any other candidates, right? I need to figure out 2 more basic variables by pivoting and choosing the right spot to pivot. Okay, so let's go to pivot. Okay, so I would first set y4 here to be the basic variable, because it was the one for the first equation. So let's say I pivot here. So I get y4, y2. Now I need to pick a new one from here, not y2, y4, some other variable, so that after I click on it, my objective function will remain non-negative. That's important, right? Because you don't want to change that fact. So you can follow the dual simplex algorithm, check between the 2 negative coefficients to see which one has the largest ratio, meaning the ratio with the smaller absolute value. Is that right? So apparently this one will be, because it's 1/3, and that's -1. So you're going to click here. Now you see you have a set of basic variables. Now this is in canonical form, right? But I have a -b. I apply dual simplex, choosing between -1 and this -1, and then I see that this one has a smaller absolute value as a ratio. It's -1. I'll click here to pivot. And now you see everything is positive here, and everything's positive here. Then I'm done. Is that clear? Is it clear? This image is so out of focus. Is it? Is it blurred? Okay, if you're far away, it looks okay. Yeah, I think it's not focused. So that's the optimal value. Your solution will be 0, 24, 0, 0, 4, and 2. Is that okay? All right, so let's put that up. Okay, let's write it down. Okay, so you want the conclusion. So the Z max, what was that? We have 96 attained at. The optimal solution is not different. 0, 24, 0, 0, 4, and 2. Okay. Any questions on that? Is it clear? And with this, we say bye-bye to chapter 5, and we move on to something new. Are we ready? All right, so that's it for chapter 5, and let's take chapter 6. Okay, let me put up. Okay, so we talk about something called integer programming. Probably the name gives away of the new situation we'll have to handle. So we'll still be dealing with linear programming, but with further constraints. Okay, so I'll do a very, very, very soft and silly, just extremely brief introduction, just to motivate. So you know the LP problems that we have set up from real life, it has probably already come to our attention that many of the variables are actually like number of pizzas you order, number of boxes you order, number of iPhones you order. You can't order 1/3 of an iPhone, is that right? You have to buy 1 or 2. Cannot do anything between, meaning the variable of your problem actually can only take integer values or natural number. No fractions allowed. Okay? Now we're going to take that into consideration and see how that changes the whole picture. Okay? That is actually very, very bad. So the new situation will be now variables x1, x2 of xn now can only be integers. Okay. So what will be your reaction to this new added further constraint? Let's think. Say I have an LP problem with this constraint, new constraint. I don't know what to do with it. Let me neglect it. I solve with my LP assistant with simplex algorithm, and I find an optimal solution. Okay? And the optimal solution, well, unfortunately, does not take integer values. What do you do based on that? So let's say, totally just for illustrative purpose, let's say I have, let's draw the domain as in a 2D so I can illustrate the idea. Let's say I have a feasible region. I have one constraint was like this. I had another constraint was like that. And it turns out this was the optimal solution without thinking integer number for the x and y. And then I went to check and I find out they are not integer. Let's say I have 1 here, 2 here, 1, 2, and let's say 1 and 2 and 3, 1, 2, 3, just to illustrate. So if they have to be integers, then you know only these grid points are allowed. Is that right? So actually the allowed solution are these discrete points because I can't take fraction numbers. Okay, so let's say this is the feasible region. I have this my feasible region. Okay. So what will be your like instinctive approach? What will I do? Let's say just totally for the sake of arguing, let's say I have x star. Let's say just some number 2.2 for example, and I have 1.3. Let's say that's my optimal solution without having to make them integer. What will be your like naive and instinctive reaction? Any suggestion? Anyone want to comment? Let's say if this were the optimal problem without thinking it's being integer, would the following be reasonable? Could I search for an optimal solution nearby this one that shall be pretty close to the optimal? Is that a reasonable thing to think? Let's say I guess all the points for this one between 2 and 3, a combination, and this one between 1 and 2, combination. So 4 points nearby, taking integer coordinates. I can go and check if any of them is good. And hopefully that will solve my problem. So if you go there and you find out, and then you find out it's these 4 problems, 4 points, right next to the old optimal solution. Is that right? And then you go about and verify if any of them is feasible, and you find out that none. All of them are not feasible. So what do you find? All these points. So let's say 2, 1, 2, 2. Okay, it's silly that I'm putting actually number on it. The are all not feasible. Whoops. So that idea was apparently too naive, isn't it? It's not that simple. Okay. So what I want to say to you is that this is actually a pretty complicated problem mathematically, theoretically. It's very hard. There has been some algorithms proposed and some works decently well for situations, and there is not a unified agreement on what is the best algorithm, and convergence result is very complicated. Let's say the search for the optimal strategy to solve this problem is still ongoing. Okay, just to give you the state of the art for this. So I want to say, let's just write that. This is a very hard problem. Okay, so what we will do will be taking two methods that kind of are pretty popular, and it's being used, and we try to learn them. Is that okay? So in the book there is chapter 6.2 with the many applications that eventually ends up with the integer programming. But I think we are pretty convinced that this comes. So I will just let you bedtime reading. Is that okay? Very nice to put you to sleep. Yeah. Okay. So I'm going to go into the next chapter, 6.3. Introducing one method. Just kind of barely introduce it because we don't have time today. So Gomory's cutting plane algorithm. Okay, so let me set this up. So what I'm doing here, I will consider a pure, okay, so pure, I say that, integer programming. So what do I mean? It's a standard linear programming problem with additional things. So that is, so this is a LP problem with integer coefficients. Okay, all the a's are integers. I don't want square root of x1 appearing, for example, and integer coefficients and integer variables. Okay, all the variables taking integer value. Okay. So here's the idea of some kind of a setting for algorithm, but there are a lot of details we'll have to fill in. So the algorithm is the following. So you give me an LP problem with the additional constraint on the variable. First, I neglect your integral constraint. I just solve it. So solve, I cannot spell. Solve LP, neglect integral constraint. Okay, and then I look at the solution. If they are all taking integer values, then I'm really lucky, I'm done. Is that right? Okay, so if optimal solution is integral, then that's really great, done, and you stop, you're done. Okay, if not, and then I need to do a lot of work, okay, potentially. So what is the idea will be the following. I will be adding a new constraint. So the idea will be I will be making my feasible region a little bit smaller, take small steps, such that the smaller feasible region in the end will give me an optimal solution that's integral. Is that clear? So I will have to add a new constraint. But then this constraint has to be added in a very smart way. So, okay, with the following properties, it must have the following property. So first, after adding the new constraint, X star must be not feasible. It has to make the X star going out of the feasible region. Otherwise, that's still the optimal solution. You didn't do anything. Is that clear? So X star must not satisfy the new constraint. And then second, so which means I need to remove the part containing X star in my feasible region, at least part of it. But then I cannot remove too many of them because, you know, I have all these grid points that are feasible. Any of them is a potential candidate for the optimal solution. So when you are adding a new constraint, you cannot remove any of these points. Is that right? Because otherwise you lose something. You should keep all those still in. So all integral feasible solution, okay? Let's see, this is all word of the old LP, okay? They must remain feasible. Okay, with the new constraint. Okay, so how do you actually add such a constraint? We will talk about it. That's the big step, finding the constraint to add. Okay, so once you have done that, and then you solve the new LP with the new constraint, again neglecting the integral constraint, and to see if you find a new optimal solution and check if it's integral or not. If not, then you have to repeat until you find one. Is that clear? So the big step is here, how do you come up with a new constraint? Okay, so we'll talk about it through an example. So let's try that. So is it clear the key idea, the basic like kind of a philosophy behind this? Mm-hmm. Okay, so we have about 15 minutes. I won't be able to finish this example, but let's get started. And next time we'll continue. Okay, take an example with the two variables. You see the new thing here, highlighted, and integral. Oh no, I should not do that. I thought it's a highlighter and it actually erases. I'll block it, and integral. Okay, if I write this, you will know that problem would take a lot of work to solve. All right, so let's follow the setting, at least the first step. We know what to do. We can set this up in a Tableau and can solve it. Okay, so this is a small problem with two variables. The reason for that is, in the end, I can draw in the graph, right, the feasible region, what we're actually doing. So you see clearly what does it mean by cutting plane. Okay, if I take three variables, then I cannot draw a 3D object for you. Okay, so let's say we set up the Tableau. So you add two slack variables, x3 and x4, into it, and 1, -1, 1, 0, 2, 2, 4, 0, 1, 15, and then you see that they naturally serve as your basic variables, right? That's very nice. And then they have 1, -3, 0, 0, 0. That's your initial Tableau. So this is regular simplex. So I check that's negative, and then I look among all the coefficients here, pick only the positive one as my candidate. There's only one. So there you click. Right, imagine you're in LP Assistant. So I switch x2 with x4 as my basic variable. So I get these nasty fractions: 3/2, 0, 1, 1/4, 23/4, 1/2, 1, 0, 1/4, 15/4. 5/2, 0, 0, 3/4, and 45/4. Okay, so one step of pivoting, I see that I already have optimal solution because these are all non-negative, and that's the optimal solution obtained at, that's the optimal solution, that's the optimal value. And I see that they are fractions, right? So they're not integral, so it's not good. X star in here will be 0, 15/4, 23/4, and 0. It's not integral. Okay, so I have to deal with it. Okay, I need to come up with some new constraint and make some changes. So hopefully the change will eventually lead to integral optimal solutions. Okay, so how do I do the change? So I will go, so here I will just present to you the algorithm, and we'll look into details later. We'll have more examples. Okay, so I will look at the optimal solution. These will be here. Look at one and pick the one that has a fraction in it. Here, each, and they both have a fraction, right? So this will be actually 5 plus 3/4, and this will be 3 and 3/4. Is that right? And you can pick any of them. We'll be fine. Okay? So pick a row with, let's say, non-integral BIs. Okay, say I can pick the first one. Okay, so I'm going to deal with this guy here. I try to make this eventually to be integral. Okay, let's see what one can do. Let's write out that equation. So what does that equation say? That says 3/2 x1, right? 0x2 plus x3 plus 1/4 x4 equals 23/4 with all these fraction numbers here. Okay, so what I do next will be I will split all these fraction numbers into an integer part plus a fraction. Is that clear? That fraction is between 0 and 1. Okay? So right now we don't so separate these numbers. Are they called improper fraction, where the numerator is bigger than the denominator? Yeah. Improper fractions. Okay, so too many words. Let me show you. So this is breaking up into 1 plus half, x1, x3 is there, 1/4 is there, and this is breaking up into 5 and 3/4. Is that right? Okay. So now the fraction part has to be positive, okay, between 0 and 1. Okay, we'll go back into that in detail. And now I am going to rearrange in the following way. That is, everything containing fraction stays on the left-hand side. Everything containing integer coefficient go to the right-hand side. Is that clear? So what I will have remain here will be a half x1. That will be a fraction. That's an integer, and that's a fraction, 1/4 x4. And then I have 3/4, that's a fraction. Okay? And everything else goes to the right-hand side. 5, and then I have an x1, and then I have an x3. Is that okay? I separate them. Okay. Now you see, these are all integers, and x1, x2, x3, these are variables that are integers, right? So look at the right-hand side. What do I have? They're all integer numbers you're adding and subtracting. So it has to end up with an integer number. We agree? So the right-hand side must be integral. Okay, it equals to some integer. So what does it mean to the left-hand side? It equals to that, so it must be an integer as well. Is that clear? This is the reasoning, arguing part. Okay, so we conclude that the left-hand side must be integral as well. It must equal to an integer. And then here I have a question here. What is the smallest value, integer value for left-hand side? It equals what? Would you be able to figure that out? So now, by the way we are setting this up, we know x1, x4 are bigger than 0, integers, right? And this is a fraction that's between 0 and 1, positive. And this is a fraction between 0 and 1, positive. So this should add up to be a positive number. Is that right? And this will have to be a minus sign, subtracting something that's positive, because I always take the positive fraction part to move over. So what do you think this subtraction, what will be the smallest integer that can come out of this subtraction? 0. Is that clear? The smallest value the left-hand side can take as an integer is 0, because it has to be an integer, because it equals something that's integer, right? So the left-hand side will be integer and will be bigger than, equal to 0. So doesn't that sound like the property of all the variables that I have in this system? They are bigger than 0, they're integers. So how about I call that a variable? Now I introduce a new variable that's bigger than 0 and integer. I set it to equal the left-hand side. That becomes my new constraint. So let's write out details and see exactly what does it say. So set it, and then I know x5 is bigger than 0 and integral. Okay, so this becomes my new constraint. Let's look at it. Okay, so I have a half x1 plus and fourth x4. Let me move the 3/4 to the right-hand side and move the x5 to the left. That's the new constraint. And if you put that into the together with all the other constraints, if you're thinking about the algorithm, the simplex algorithm, you see you introduce a new variable, and now it has a negative sign in front of it. I would very much to have it as a plus sign, so this becomes the basic variable, right? So let's do that. I will just multiply -1 everywhere. So this will get a negative number. This is a negative, and now this is positive, and then I have 3/4. Okay, so where's my old problem? Yeah. Okay, so we can summarize. Now I have a new LP problem with all the slack variables. So I will have this minimizing. I need to take from the final tableau 5/2 x1, x2, x3, x4 plus 3/4 x4. Is that right? Minus 45/4. So this is taken from the final tableau over there. Okay. Subject to. Okay, let's copy 3/2 x1, x3, 1/4 x4 equals, oh, there's an x5, give me some space, 23/4 half x1 plus x2 plus a fourth x4, 15/4 negative half x1, that's the new one that we have now, negative a fourth x3 plus x5 equal negative 3/4. Okay, and x1, x2, x5 now is bigger than 0 and integral. Okay, so the new variable you added, x5, is bigger than 0 and it takes only integer values. Is that clear? Okay, so what do you do? Well, you see, it's in canonical form with the basic variables. These three are your basic variables, and you can give it into to LP Assistant, and you can solve it with the dual simplex, right? Why do we need to use dual simplex? Because I have the negative sign on the B, one of the B. Is that right? And you can solve it, and then you look at the optimal solution and check if it is integral. If yes, you're done. If not, you have to repeat. Find a new, further constraint. But we don't have time today. Next time we'll finish this example. Okay. So do we get the rough idea now? All right.